Clustering or cluster analysis is a methodology that is used in machine learning to group similar objects into groups that we call clusters. There are many algorithms for clustering, each with a different purpose and technique. Today, we will study one of the most popular clustering algorithms, the k-means. Its popularity can be explained by its simplicity and because of its intuitive algorithmic design that can be understood with little effort. It has been successfully used in many distinct applications, such as market segmentation, computer vision, and astronomy, among many other domains. In clustering, we consider the existence of data points, which we can also call observations or simply elements. Each observation is characterized by several dimensions. For example, consider that I want to group the users of Internet services into several clusters. Each user will be an observation object and will be classified by several characteristics that we can also call features or dimensions. We will consider two features, the age of the individual and its Internet consumption. Note that in clustering, we do not typically reflect only upon a single dimension, but on several dimensions. This is different from when we look at the frequency distribution or when we examine a unique box plot for a single variable in descriptive statistics. Note that so far I have only discussed about numerical data and not categorical data. I monitored dimensions that can be counted, such as age, or that can be measured on a scale, such as the Internet consumption. If I wanted to inquire about the social status of the person, such as upper class, middle class, or lower class, this would hardly be put easily on a scale. We cannot say with certainty that the upper class is above the middle class or that the lower class is below the middle class. In other words, there is no concept of order or numerical meaning in the data, because it is categorical. We cannot easily assign numbers to the social status and still capture the overall meaning of the data. We could instead monitor the salary of the person, which is something objective that we can measure. Then we could say something about the relative value of people with different salaries. Since to apply k-means, we need to calculate the distance between two observations, in this case people, there needs to be a special mathematical meaning associated to each value that characterizes an observation, which in our case is a person. There are ways to make clustering work with categorical data, but for that we need special distance functions, as we will see. In general, it is best to use numerical features only. For simplicity, we are only going to consider clustering examples either for one feature and the problem is unidimensional, or for two features and the problem is multidimensional or two-dimensional. The idea is, however, the same if we include more dimensions. But why do we need clustering for? Let me give you an example. It could be useful for the Internet company paying for a small survey to cluster their customers into 2 or 3 groups to see how their clients can be distinguished by their age and consumption of Internet in simultaneous. If I find a group with low age and high consumption, I could try to target this group with a specific marketing campaign to award their loyalty to the company. Seemingly, if I find a group of older clients with low consumption, I could target this group in specific with a campaign to inquire why is that they don't use so much the internet service. The classification of observations into groups requires some method for computing the distance, or in other words, the dissimilarity between each pair of observations. There are many approaches to calculate these distances, and the choice of distance measure is a critical step in clustering. It defines how the similarity of two observations is calculated, and it will influence the shape and the size of the clusters. The classical methods for distance measures are the Euclidean and the Manhattan distances. However, alternative distance measures exist, such as the correlation-based distances, the Gower distance measure, which is commonly used for datasets containing categorical and ordinal features, and the cosine distance. So, how do you decide on a particular distance measure? Unfortunately, there is no straightforward answer for this question, and several considerations come into play. The Euclidean distance, or also called the straight line distance, or as the crow flies, is a reasonable measure to use if your features follow an approximate Gaussian distribution. Since the Euclidean distance forms spherical clusters, we can capture the data with more or less ease. However, if your features deviate significantly from normality, or if you just want to be more robust to existing outliers, then other distance functions can be better choices. We can represent the data that we have in the two-dimensional space if we have two features only. We have the x-axis and the y-axis. In our example, the x-axis represents the first dimension of h, and the second dimension, or y-axis, represents the internet consumption. Each data point represents a person that answered the survey. If we consider more than two dimensions, it is more difficult to visualize the data. We can still see it relatively well with 3 dimensions, but after that it becomes more abstract. The algorithm works well in any case and gives good results, but it becomes harder for us to visualize for higher dimensions. In a similar manner, it is also possible to apply k-means to a single dimension and disregard any other dimensions. It also works. For example, imagine that I only consider the h factor. In that case, we could see the data points scattered around the line. This could help me understand that in terms of age, we have, for example, 2 groups, one from 20 to 60 years old and another above the 60 years old. The same for internet consumption. By searching for 3 groups, I could find that the consumption is either low, below 5 gigabytes per month, medium, or high, above 25 gigabytes. This information could help the company set their monthly limits and adjust their internet offering packages. As we have seen, and one of the most common applications of clustering, in general and not just for k-means, is customer segmentation. This strategy is used across different fields, including the telecom, as we have talked about, banking services, online commerce, sports, advertising, and in general sales. There is another application of clustering. Let's say you have multiple documents and you need to cluster to group similar documents together. Clustering helps us to group these documents such that similar documents are in the same clusters. To cluster documents, each document is an object, characterized by several dimensions, such as number of pages, number of figures, number of sections, number of times a certain word shows up, and other features. We can also use clustering to detect objects in images. Here we try to club similar pixels in the image together. There are many more applications that I'm sure you have already thought about. You can share these applications in the comment section below, for example. The idea of k-means is to create clusters of data points, or observations, according to similarity. The idea is a bit tricky, especially if you need to think in more than one dimension, but let us start by thinking in one dimension only. Imagine that I surveyed 3 people, one with 21 years old, another with 22 years old, and the third person with 80 years old. It is quite clear how to group them into 2 clusters, right? The 2 youngest will go into one group, one cluster, and the oldest will go into another group. I can make these calculations again because I am using a numerical variable that is age. But what if I had the 2 younger clients with a large consumption and the oldest with a low consumption of internet? How would I group them? The same way, right? The young and high consumption clients in one group and the old and low consumer in another group. What if the 2 youngest had a low consumption and the oldest had a high consumption? Would the clusters change? Not exactly. This follows from the fact that the group of youngest still share 2 properties, which in this case are the age and the low relative consumption. But what if we had many more dimensions and a more complicated setting? How can we group our data rigorously? I can try to make groups of objects by guessing, but then how can I evaluate their quality? I won't be able to see them easily in a very high dimensional space. This is in fact possible, using other techniques such as TCNA, but for now let us keep it simple. This is where we can make use of evaluation metrics. Let's discuss 3 of them and understand how we can use them to evaluate the quality of our clusters. After we have decided on our clusters based on an informed or less informed guess, we can evaluate them in terms of inertia. Inertia tells us how far the points within the inside of a cluster are from each other. In practice, we can calculate the inertia as the sum of the distances of all the points within a cluster from the centroid of that cluster. And the centroid is the virtual data point that stands in the center, so it's the center of the cluster. In the example with one dimension, the age, we have a cluster that includes the 2 younger clients with 21 and 22 years old. So we have the centroid at 21.5 years old. That is the centroid, but it doesn't necessarily correspond to an existing age in the dataset. To measure the centroid, just take the average per dimension of all the data points inside the cluster. The sum of the distances of the 2 youngest will be 0.5 plus 0.5, because 22 is 0.5 away from the centroid, that is 21.5, remember? And 21 is also 0.5 away from the centroid. For the other cluster, the centroid equates the oldest client, that is 8 years old, and the distance is 0 in this case. The final inertial value for our simple clustering is the sum of all these distances, which is 1, so 0.5 plus 0.5 plus 0. The distance within the clusters is also known as intra-cluster distances, so inertia gives us the sum of intercluster distances. Now, what do you think is a good value for inertia for a good cluster? Is a small inertial value a good value, or do we need a large value? We want the points within the same cluster to be like each other, right? Hence, the distance between them should be as low as possible. Keeping this in mind, we can say that the lesser the inertial value is, the better our clusters are. We now know that inertia tries to minimize the intra-cluster distances. But there is another important property in clustering. Can you guess what that is? It relates to how different clusters should be as different as possible from each other. This is where the Dunn index comes into action. Along with the distance between the centroid and the data points, the Dunn index also considers the distance between the clusters. This distance between the centroids of different clusters is known as the inter-cluster distance. Let's look at the formula of the Dunn index. The Dunn index is the ratio of the minimum of inter-cluster distances and the maximum of intra-cluster distances. The formula is a bit complicated in terms of interpretation, but essentially we want to maximize the Dunn index. The more the value of the Dunn index, the better our clusters will be. Let's understand the intuition behind the Dunn index. In order to maximize the value of the Dunn index, the numerator should be as large as possible. In a maximization context, that is always the case with fractions. Here we are taking the smallest distance between the clusters. The groups should be as far apart as possible, so we consider the worst case, the minimum distance between two clusters. Also, the denominator should be minimum to maximize the Dunn index. Here we are taking the maximum of all intra-clusters distances. Again, the intuition is the same. The observation points within a cluster should share as much as possible the same properties. So we search for the 2 points within a cluster that are the farther away. So, the idea is to divide the smallest distance between clusters by the largest distance within a cluster. This formulation has a peculiar problem in that if one of the clusters is badly behaved, where the others are tightly packed, since the denominator contains a maximum term instead of an average term, the Dunn index for that set of clusters will be uncharacteristically low. This is thus a worst-case indicator, and that has to be kept in mind. In k-means clustering, we partition observations into a set of k mutually exclusive groups, that is, the clusters. By mutually exclusive, I mean that the same observation cannot stay in the same two groups at the same time. In other words, two groups do not share elements. We have the 8 points again from our example relative to the age and the internet consumption, and we want to apply the k-means to create clusters for these points. Here's how we can do it. The first step in k-means is to pick or to select the number of clusters k. You always need to set this number in k-means. In other algorithms you don't need to do that, or the parameters that you need to handle or to configure have a different meaning. However, in k-means you will need to know the best k in advance. With many dimensions this can be quite a problem, but let us continue. We are now going to randomly select the centroid for each cluster. Let's say we want to have 2 clusters, so k is equal to 2 here. We then randomly select the 2 centroids. We typically select a data point from the dataset in the initialization step. Here, the red and green circles represent the centroids for these clusters. We picked a young person for cluster 1 with a high consumption and the oldest client with a lower consumption for cluster 2. Once we have initialized all the centroids, we assign each point to the closest centroid. Here you can see that the points closer to the red point are assigned to the red cluster, where the points closer to the green point are assigned to the green cluster. Note that we can see right away that the lowest red point is perhaps misclassified. Do not worry, the algorithm itself will fix this later. After all, the centroids were selected by a lucky guess, and sometimes we can be lucky and sometimes not so lucky. Now, once we have assigned all the points to the clusters, the green and the red one, the next step is to compute the centroids of the newly formed clusters. Here, the red and green crosses are the new centroids. Remember how I said that centroids do not necessarily need to be an existing object or observation? They only need to be at the center of their cluster, and that is the case here. The final step now is to repeat steps 3 and 4 for many iterations. But wait, when should we stop this process? It cannot run until eternity, right? There are essentially 3 stopping criteria that can be adopted to stop the k-means clustering. We can stop the algorithm if the centroids of the newly formed clusters do not change over time. Even after multiple iterations, if we are getting the same centroids, we can say that the algorithm is not learning any pattern and it is a sign to stop the training. Another clear sign that we should stop the learning or the training process is if the points remain in the same cluster even after training the algorithm for multiple iterations. Finally, we can stop the training if the maximum number of iterations is reached. Suppose we have set the number of iterations as 100. The process will repeat itself for 100 iterations before stopping. So we are now at the end of our lecture. Thank you for watching and staying with us, supporting our project. And for the next lecture, we will talk about real-world applications of k-means.